All right, good morning. Hope everyone had a good weekend. Today, we are going to wrap up the stuff on uh, integers and divisibility, greatest common divisors, and some modular arithmetic. And that's going to form the foundation of the mathematics that we need to know in order to move forward. We're not going to use all of it all the time, but there'll be some instances where we're just exploring some puzzles or exploring permutations. And it comes up that in order to really make sense of what's going on, we need to know some results about divisibility, or we need to know something about a greatest common divisor. And so that's why we're just refreshing our memories with all of these topics. Refreshing our memories in the sense of divisibility and whatnot, since we've been dealing with since elementary school, but there might be a few new nuggets of new information that is worth knowing as well. All right, so let's get into where we left off. We just have covered the division algorithm. And the division algorithm it's really just a statement that says if you have two numbers, you can always divide one of the numbers by another one. And if it doesn't go in evenly, then there'll be some remainder left over. And so how many times, in this case, how many times b goes into the number a is given by the quotient q, and what's left over is given by the remainder r. What we ended up finishing off with last day was just a demo of this in Sage Math, where I said these kinds of commands were built into most programming languages. So this was if you have the number 43, how many times does 8 go into it? It goes in 5 times. And then the percent operator is the remainder operator. So 43, when divided by 8, what's the remainder? The remainder is 3. And this can be done in Sage Math, all in one statement called divmod. So that's where we ended off with last day. Lecture recordings are available right on the course website. So I'm just taking a glance at the chat window. I will bring that up here. So on the course website, we go to lectures, then the recordings are listed right here next to the corresponding lecture. Okay, so last recording, which was the set theory stuff, there'll be a little bit of set theory in there, and then we would have gone into the properties of integers and whatnot. So some of this recording contains the beginning part of this appendix, and then today's recording will be posted there, and that contains the remaining part of that appendix. All right, so let's have a look at how this division algorithm is going to be useful for us in the context of computing GCDs. Now, I mentioned last day that the idea is to try to compute GCDs, and this is a big thing, without factoring. We don't want to have to factor a number into its prime factorization and do that for a second number, and then try to figure out what the GCD is by looking at all the common prime factors and the highest powers to which they appear in both decompositions of the numbers. It turns out that that's too computationally intensive, and in fact, factoring is a very difficult problem in general for integers, especially large integers. So if we can do GCDs without factoring, then that would be absolutely wonderful. And it turns out we can. And here is the main idea with doing a GCD without factoring, and that's given by this lemma, which I've called lemma b.1.2. So suppose that you have two numbers a and b, and you do the division algorithm on them. So you figure out how many times does b go into a and what's left over. So b goes into a q times with a remainder of r. Then the claim is that if you originally wanted to find the GCD of a and b, so this is what you originally wanted to find, well, it turns out that that's equal to the GCD of b and r. So, and if you think about what r is the remainder of the division. So r has to be smaller than a. So we reduced one GCD computation with potentially bigger numbers, A and B, with a new GCD computation, where one of the numbers is now smaller. B is still the same, but the number A has been replaced by the number R, which is now smaller. And so that's the idea, is we can replace one GCD calculation, I don't know why that's such a tongue twister, with another GCD calculation that involves smaller numbers. So let's see why this is true. So let's prove this result. So in order to prove this result, I want to show that the GCD of A and B is the same as the GCD of B and R. What we'll do is we'll just let D be the GCD of A and B, and G be the GCD of B and R. So let's just call those GCD something. And so our ultimate goal is to show that D and G are the same number. So D is equal to G. So that's our goal. Let's show that D is equal to G. So how are we going to do that? Well, the way we're going to do that is we're just going to go ahead and apply the definitions that we have in these cases. So we know that D is the greatest common divisor of A and B. So that means that D divides A and B. So I'll write it like that. D divides A comma B, so it divides both A and B. So now what can I conclude? Well, that means that D divides, if it divides A and it divides B, then I'm going to look at this relationship I have, because this is really the only other thing I have to work with. I have this relationship that A is equal to BQ plus R. So if D divides A and D divides B, then it divides two of those terms in that equation. So it must divide the third one. So D must divide A minus BQ, because it divides A and it divides B, but that's equal to R. So what we have is that D divides R. So now we know that D divides B, D divides R, and so that means that D has to divide both B and R. So it's a common divisor of B and R. So the GCD of A and B is also a common divisor of B and R. But G, little g, is the greatest of all common divisors of B and R. So D, being a common divisor of B and R, it can't be bigger than G, because G is the biggest one possible. So that means that D has to be smaller than or equal to G. So we have this relationship now between D and G, and that is that D can't be bigger than G. But now we can apply the same argument in the opposite direction. We can do the same thing now by saying, okay, well, G, that divides B and R. So it divides two of the terms of the equation that relates A, B, and R, the equation that's given in the lemma from the division algorithm. So if it divides B and R, then G must divide BQ plus R, because it divides those two terms, so it has to divide the sum. But that's equal to A. So that means G has to divide A. And again, we have that G divides B, G divides A. So that means that G divides the two numbers A and B. So it's a common divisor of A and B, but D was the biggest of all common divisors. So G can't be any bigger than D. And that's our conclusion. D has to be smaller than or equal to G, but G also has to be smaller than or equal to D. And the only way those two inequalities are going to be satisfied is, so that's a therefore, the triangle of dots means therefore, G is equal to D. So I'll write that in quotes just for now. This is just a shorthand save from having to write a lot, but it ended up, in this case, I had to write more because I had to explain what the triangle of dots mean, but in the future, I'll just write the triangle of dots to abbreviate for therefore. So therefore, G is equal to D, and we are done. Okay, so the division algorithm allowed us to relate A, B, and R by a single equation. And then just following through with this calculation, we got that common divisors of A and B also have to be common divisors of B and R and vice versa, and therefore the greatest common divisors had to be the same. So how does this help in computing greatest common divisors? That's what I want to show next. So let's do a GCD of, let's say, 210 and 154. Now, I want to just contrast this with, we've done some GCD calculations earlier on, and at least on Friday's lecture, but there we did factoring. The numbers were small, we factored, we found a GCD. But that was just to get sort of warmed up with the idea of what the GCD was and potential ways for computing it. Now we want to compute GCDs in a much more effective way. So what's the more effective way? We're going to use this previous lemma that says I can always replace the GCD of A and B with the GCD of B and the remainder of A divided by B. And those are going to consist of smaller numbers. So let's see what we can do. The first thing I'm going to do is I'm going to say, okay, let's do the division remainder. 154 goes into 2010, goes into 210. How many times? Well, it goes in there once. So that's our Q, with a remainder of 56. So that's our division algorithm applied to the two numbers, 210 and 154. The key here, and this is really where that lemma follows from, and this whole argument and computation falls from, is that this one equation tells me that if I have a divisor of these two, so something that divides 210 and 154, it must also divide that number there. So any divisor of 210 and 154 must also divide 56. That's what this equation is telling me. There's this relationship between those numbers, and divisibility follows from this relationship. So that tells us then, or at least the lemma above, because we worked it all the way through, says that, well, the GCD then of 210 and 154 is the GCD of 154 and 56. So I'm going to get rid of these pink arrows because I'm going to use that space for the next line here. So that's the lemma, but the lemma can be applied again and again and again. So now I want to compute the GCD of 154 and 56. Well, that's going to be the GCD of 56 and the remainder of 154 divided by 56. So I write down 154. How many times does it go into, how many times does 56 go into that? It goes in there twice. That gives us a 112. And then a 112, what do I have to add to that to get me to 54? Looks like I have to add 42 to that. So there my remainder is 42. So this is then equal to the GCD of 56 and 42. And then I keep going. 56 is 1 times 42 plus 13. So this is equal to the GCD of 42 and 13. And then I keep going. 42 is 4 times, oh no, let's see, what is it? 42 is, did I get these numbers right? 42 is, oh, it's not 13, that's why. Let's see. That's because it was 56 here. Okay, sorry. I wrote down 55 and should be a 56 there. That 56 carries over to that spot. Okay, now we're in good shape because this is now going to be a 14. And so now I need to know how many times does 14 go into 42? That goes in there 3 times, and 0's left over. So that's equal to the GCD of 14 and 0. And it's at this point where I now have a GCD that I can easily calculate. The greatest common divisor of 14 and 0? Well, it's got to be 14, because 14 divides into both 14 and it divides into 0. So it's a common divisor of both of those, and it's the biggest one possible. So we got our result. And our result, all it depended on was just division throughout. Oh, did I write down the 14, 13 there? Thank you. Yeah. Sorry, I wrote down a 14 there, but it was 13 there. It should have been a 14. Thanks. And so our GCD calculation, all it depended on was doing division and remainder. There was no factorization required. It was just division, remainder. And we got it down to a point where we got our original GCD calculation replaced by a simple one involving a number and 0. And that gave us our result. And this technique is known as the Euclidean algorithm for computing GCDs. So that's the statement there for the Euclidean algorithm. You want to find the GCD of A and B, you continue to do those steps that we just did. Now, because it's so repetitive, it's actually very nice to implement in a computer algebra system. So what we're going to do is we're going to implement the GCD calculation as an algorithm. So we will learn about all these commands in the first tutorial and then subsequent lectures as well. But for right now, I'm just going to give a demo by just doing it. So I'm just looking at the chat. No, the Euclidean algorithm is the one that's used, and I'll show you why. So here's the definition, and we'll call it the GCD. Sorry, I've just got a bit of a dry throat, so I'm drinking tea to help with it. Okay, so we've got our GCD calculation. What is it? Well, we've got two numbers in, and what we're going to do is we're just going to run the algorithm while the B number is, we'll say bigger than 0, because it's always going to be positive. So while B is bigger than 0, let's just run this algorithm. And what is it that we're going to do while B is bigger than 0? Well, we're going to do the same thing that we just did by hand. So we started with A and B, and we just updated them each time. So let's go back to what our calculation was. So in order to find the GCD of A and B, we ended up just replacing the A value with the old B value, and then replace the old B value with the remainder of the division. So we just did an update. So we took the old B value and we set A is equal to that. And then for the B value, we took A and we found the remainder when division by B happens. What value did we return in the end? We just returned the A value in the end. Again, let's just take a peek at our calculation to see that's what we did. So our last GCD was when B was 0, and the value we returned was the A value as our GCD. And so that's it. That's the Euclidean algorithm. No factorization required or anything. Let's just load it in. And now we can compute a GCD. We will compute the GCD of the one we just did, where the values 210 and 154. And there it is, 14. So this is whenever there's a GCD calculation being done, this is the algorithm that's being used. I'm just checking the chat again. So yeah, question is, does this algorithm always go to 0 in the sense that these b values, are we ever going to reach 0, or do we run into an issue with there being stuck in a loop? And let's just see what happens. So each time we did a division, so we started with 154 as our b value, and then we divided that into a, and then we took the remainder. That remainder has to be smaller than 154, because if it wasn't, then that means 154 could go more times into 210. So this 56, or maybe I'll look down here, this number has to be smaller than this one. So these things have to decrease. And they have to keep decreasing. They got to get smaller and smaller and smaller. So if I'm looking at that and I say, well, that 154, each stage I do this division and remainder, it's going to decrease. I know it's at worst going to take me 154 steps, because that number's got to drop every time. A worst case scenario is going to drop by 1. So it's got to drop every time. In fact, it won't drop by 1. It'll drop by more, but it's got to drop by at least 1 every time. And so it's going to end. This algorithm will terminate. Okay, so that is our Euclidean algorithm. One could conceivably just put this all on one line and we're done. So Euclidean algorithm implementation is like a one-line algorithm in a computer algebra system, which is really nice, super fast. No factorization required. Okay, so that's it there. Again, just for your reference. We have a built-in, SageMath has a built-in GCD algorithm, the same one, but it's just built into it. So you don't have to define this function. You can just use GCD on your own. Okay, the other thing I want to conclude from the Euclidean algorithm, which is extremely useful for us. Now I'm going to cheat a little bit here, and I'm just going to cut and paste. So I'm going to cut or copy and paste because I want these same steps to appear here so I can do a little bit more with them. And I'm going to delete the pink stuff. Okay. I'm going to also update that 14 and get rid of the other pink stuff as well, so that we can just focus on the new stuff here. Okay. The next bit I want to do with this algorithm is I want to show that we can actually do something with this GCD and its relationship with the original two numbers. So it turns out that the GCD we can always write as a linear combination of the original two numbers. Let's see how we can do that. So the first thing I'm going to do is go to the division algorithm equation right before we had the 0 introduced. This one had our GCD appearing by itself as the remainder of some step. If I take this equation and just rewrite it, so let's just rewrite it. I'll put it over here and say 14, solve for that, is equal to 56 minus 1 times 42. So I've just rewritten it by solving for 14. So this allowed me to write 14 as a linear combination of 56 and 42. And now the previous equation allows me to do something with the 42. So if I take this expression for 42 and plug it into here, then what I get is that 14 is equal to 56 minus 1 times, what is 42? 42 is 154 minus 2 times 56. So I've just replaced the 42 with what it is in terms of 154 and 56. Let's just collect some common terms together. So that's minus 154, and that's a plus 2 times 56. Or in other words, 3 times 56 minus 154. So that gives us 14 is 3 times 56 minus 154. Now 56, Maybe I'll pick one more color here. 56 can be rewritten in terms of 154 and 210. So I'll take that 56 and I'll come in from the top with that so that I don't obscure where I want to write. I can plug it into there. So I get that this is 3 times 210 minus 154. And then that's minus 154. So I've just plugged in for 56, the fact that it's 210 minus 154. And when I do that, I can now write it in terms of 210 and 154. So that's 3 times 210. And then minus 3 times 154 minus, so it looks like it's a minus 4 times 154. Maybe I'll put parentheses around those. And so what we conclude here is that 3 times 210 minus 4 times 154 is equal to 14, which is the GCD of 210 and 154. Okay, so you may think, well, big deal. What did we actually do here? We started with two numbers, 210 and 154, and we showed we can get a combination of them equal to their GCD. And that actually turns out to be quite a big deal, that you can always take any two numbers and whatever their GCD is, you can always find a linear combination of those two numbers to actually obtain the GCD. This is known as the extended Euclidean algorithm, the techniques we've done here to get these two values, 3 and -4. And so the extended Euclidean algorithm tells us that if the GCD of A and B is D, then we can always find two numbers. In this case, it's U and V, which we call them, such that A times U plus B times V is equal to D. So I just want to show you that this is implemented already in SAGE. It's known as XGCD, so extended GCD. And we can do it as 210, 154. And what gets returned is the GCD, the number that you would multiply to the first number that you inputted into XGCD. So this tells me that 3 times 210 plus -4 times 154 is equal to the GCD of 14. So this is also a nice algorithm to have to be able to produce these values, the extended Euclidean algorithm. And that we'll see over a few examples, and then also on the homework assignment, turns out to be quite a powerful tool to have, that you can always, for any two values, when you get their GCD, you can also get a linear combination of the two original values to produce that GCD. Okay, so let's see maybe where some places are that it's useful. Okay, so I'm going to get into the definition of a prime. You've probably learned about prime numbers since grade school. So let's just talk a little bit about what a prime number is, and then we'll see how the extended Euclidean algorithm can help answer some questions about primes. So a prime number is an integer with exactly two positive divisors, 1 and itself. So exactly two positive divisors, 1 and itself. So for example, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime. 2 is the only even prime because any other even number is divisible by 2 and 1 and itself, so it's got more than two divisors. 9 is not prime because it's divisible by 3, which is neither 1 nor the number 9 itself, and so on. So we've got all of these values which are primes. Turns out there's lots to do with primes. There's lots of study with primes. They've been studied for thousands of years, and there's still a lot to be unknown. I like that question. Is 1 considered a prime? Is 1 considered a prime? Actually, before I get to that, I see there was a previous question that said, is the converse of B.1.4 true? So I'm going to back up and look at the B.1.4. So the converse of that would be, if there exists two integers u and v such that the linear combination of them is d, does that mean d is a GCD? The answer is no, the converse is not true. Converse is not true. So for example, I'm just going to build off of my previous result. 6 times 210 minus 8 times 154 is equal to 28. So I just multiplied everything by 2. So therefore, we do have two integers, 6 and -8, such that the linear combination of 210 and 154 with those two integers as weights gives me 28, but 28 is not the GCD. There is a way to adjust the converse so that you can get something true out of it, and it really had to do with the fact that, you know, I made the two numbers u and v actually have a common factor, which sort of screwed things up. So there is a way to build a converse of this that allows you to get a GCD, but it's just not exactly straightforward in terms of the converse. You have to make sure you don't have these extra factors in the u's and the v's that will mess things up for you. All right, so yeah, so there's an answer there about a prime number must have exactly two factors, 1 and itself, so 1 would not be a prime. That's right, so that's exactly why I underlined the 2, the exactly 2 here. And so that means that 1 is not a prime. Now this, you know, is something that is quite often misunderstood. I mean, even my kids can come home from school and, you know, a teacher might have said that 1 is a prime number. And so it's still something that's sort of prevalent in the elementary school system. Some teachers make comments that 1 is prime. So it's worth stating why we don't want 1 to be a prime. Why don't I? So I built my definition so I explicitly have excluded 1 as being a prime, because I said there have to be exactly 2 prime divisors, or sorry, exactly 2 positive divisors. 1 only has 1 positive divisor, 1 itself. Why don't I want 1 to be a prime? Well, the real reason is just that we want a result known as the fundamental theorem of arithmetic to be true. And the fundamental theorem of arithmetic says that every positive integer has a unique factorization into prime numbers, so, or a unique prime factorization. If we allowed 1 to be a prime, then there wouldn't be unique factorizations, because you could insert any number of 1s as factors and get different factorizations. So for example, unique factorization, 15 is 3 times 5. That's a unique factorization. I'll use dots here. 3 times 5. That's a unique factorization of 15. There's no other factorization into prime numbers of 15. But if we did allow prime numbers, 1 to be a prime number, then we'd have to allow different factorizations. And so that statement is no longer true. A number is not uniquely factorized into prime numbers. There's multiple ways to do it depending on how many 1s you want to add in there. And that's why we don't want 1 to be a prime, because it causes our most fundamental theorem about factorization to be false. So let's throw 1 away. So 1's not a prime. In fact, 1 is special though, so we do call it a unit. So 1 is not prime, 1 is a unit. It's what we call a unit. Okay, so there's prime numbers, there's composite numbers, and then there's unit. And 1 is a unit. 9 is a composite, 15 is a composite. They're products of primes. Okay, so now with that in mind, let's prove a result about prime numbers. So what's our result? If P is a prime number and A and B are integers such that P divides the product, then it has to divide one of those two numbers, A or B. You know, this might seem reasonable. It says that, you know, 2 divides 14 times 27. Divides their product. Whatever their product is, I know it divides their product. Why? Because it divides one of the factors. It divides 14. Okay, so this is really what it's saying. If 2 divides a product, then it has to divide one of the factors. Why is that? It may seem like an obvious statement if you just think about some examples, but we need to prove it in general. And the way we're going to prove it in general is we're going to use our extended Euclidean algorithm. So what we're going to do is we're going to suppose P divides AB, but P does not divide A. Then we're going to show that it has to divide the other one. It has to divide B. So if P divides the product, but it doesn't divide one of the factors, then it must divide the other one. So that's how we're going to prove it. Then, if P doesn't divide A, then the GCD of A and P, what must that be? What must it be? Yeah, it must be 1. P doesn't divide A. So the only divisors of P are 1 and P. So a common divisor of A and P is either going to be 1 or it's going to be P. But P doesn't divide A, so the common divisor can't be P. So the only other option is it's 1. So the GCD is 1. And by the extended Euclidean algorithm, we know that there is U and V such that, so those are integers, such that there's a linear combination of A and P that's equal to 1. So A times U plus P times V is 1. That's the extended Euclidean algorithm. Linear combination has to equal the GCDs for some U and V. Now we want to bring P into the mix, so we'll multiply by B. And I get that ABU plus BPV is equal to B. And now I have that P has to divide the second term there, the BPV. P also divides the first term because P divides this. P divides AB. P divides P. So P must divide the left-hand side, ABU plus BPV. But if P divides the left-hand side, then it must divide B because they're equal. Then P divides B. And we are done. It turns out that this, I've stated it as a lemma, as a consequence of the definition of a prime, which I said a prime was a number which is divisible by exactly 1 and itself. But it turns out that this is also a way to characterize primes, this lemma. Prime numbers are the numbers that if they divide a product, they have to divide one of the two factors in that product. One of the homework assignment questions has you to show that this result is not true for non-prime numbers. So in general, if I had a number that divided A and B, it's not necessarily true that it has to divide A or B. That's only true for prime numbers. And so you're asked to give an example that shows why this lemma doesn't hold in the case where the number isn't prime. The next thing I want to talk about is Euler's phi function. It's also known as Euler's totient function. And what this does is it just counts the number of numbers that are relatively prime to n that are strictly smaller than n. So it's sort of written in what may look like a complicated way. So it says phi of n is, and I want to draw your attention to the fact that these are cardinalities. So it's the cardinality or the size of this set, where it's the set of all numbers, all integers m, where m is between 1 and n, that's relatively prime to n. So let's have a look at an example here, just to see what these things are. So what's phi of 6? So phi of 6 is, I will just list out all the numbers between 1 and 6. And I just want to count the ones that are relatively prime to 6. So that ones that have a GCD of 1 with 6. So that's not relatively prime because the GCD of 2 and 6 is 2, not 1. This is not relatively prime because the GCD of 3 and 6 is 3, not 1. That's not relatively prime because the GCD is 2, again, not 1. 6 is not relatively prime because its GCD is 6 with 6. So there's only two numbers that are relatively prime to 6 that are smaller than 6. Smaller than or equal to, but the number itself is never going to be relatively prime to itself unless it is 1. So that means that phi of 6 is 2. And we can do another one, let's say phi of 10. So I'm just going to now list the numbers. This is how I usually do it if I'm doing small numbers by listing. I just say, okay, I'm going to go through them. 1's relatively prime to 10. 2's not. 3 is. 4's not. 5's not. 6's not. 7 is. 8's not. 9 is. And 10's not. So phi of 10 is 4. Try this one yourself just by doing that. What is phi of 16? Just go through it and sort of list in your head which ones are, which ones aren't. Well, actually, which ones are is the more important ones, and count them up. Yeah, we got 8 of them. All the odd numbers. All the odd numbers will work. It turns out that rather than listing, you can work out the value of phi from a prime factorization, and that's what's shown here. Prime factorization, if you've got p1 to the power of v1, p2 to the power of v2, and so on, then there's a way to work it out by just, you drop the powers on each of the primes by 1, and you multiply by the prime minus 1. It kind of looks like a differentiation kind of rule. It's not, but if you've done calculus 1, for example, this kind of looks almost like a derivative. It's like, you bring the exponent, or you take 1 away from the exponent, and you kind of multiply by p1 minus 1. It's kind of a funny looking rule, but it turns out that this is what it is. This is what phi of n is. Okay. Now let's get into the calculations with the remainder. So we're just going to focus strictly on remainders now. The remainders that we had from the division algorithm, the remainders turn out to be a key thing in analyzing anything to do with integers. And so for that, we're actually going to come up with a special notation to denote remainders. And that's this notation here, modular notation. So we read this as a mod n, and all that is it represents the remainder when you take a and divide it by n. So for example, if I had 25 and I took it mod 7, well, I just want to find what is the remainder when I take 25 and divide it by 7. So it goes into 7 goes into 25 3 times to make 21, and then there's 4 left over. Exactly. So that symbol 25 mod 7 is representing the number 4. And we can do it with negative numbers as well. What is this? Negative 37 mod 3. And I do want to draw your attention to the fact that the remainder is the positive number. So the remainder is a positive number. Yep, so it looks like we've got it here. We've got a 2, and so we'll just jot down y. So negative 37. How many times does 3 go into it? Well, 3 can go into it negative 13 times, because that's going to give me a negative 39. And then I can add 2 to it to get negative 37. So there's my remainder. It's the positive number between 0 and strictly less than 3. Okay. Now with this modular, with this mod notation, this remainder notation, we typically use it in terms of a congruence relation. So it's more likely seen in terms of an equation like this. A with these triple equality sign, B mod n. And that just means that A and B have the same remainder mod n, or a more appropriate way to think about it is that if I take their difference, A minus B, that's divisible by n. So for example, I could say working mod 9, 67, and 22 are equivalent mod 9. We read that triple equal sign as equivalent. So 67 is equivalent to 22 mod 9. Why? That's because their difference, 67 minus 22 is 54, is divisible by 9. And so as another example, 3 is equivalent to negative 2 mod 5, since 3 minus 2 is equal to 5, and that's divisible by 5. Divisible by 5. Okay, so that's using our new notation of congruence. Turns out that this congruence equation behaves very nicely in terms of arithmetic. So for example, if I know that A is congruent, I should have had triple equal signs here. I'm all right if you use just a regular equal sign. Triple equal signs is more typical, but just basic equal signs are fine as well. So this says that A is equivalent to C mod n. So A minus C is divisible by n, and B minus D is divisible by n. Then what we get is that A plus B has to be equivalent to C plus D mod n, and A times B has to be equivalent to C times D mod n. So for example, if I had, if I have like our previous, well, maybe I'll do it this way. 3 is equivalent to negative 2 mod 5, and 10 is equivalent to 15 mod 5. Then that means I could add up the equations and get that 13 is equivalent to 13 mod 5. And we can use these equations to produce other ones. And that's really nice because it allows us to do questions like the following. And so this is our last example for today, but here's the question. We are going to show that 2 to the 74 plus 3 to the 74 is divisible by 13. Now, I deliberately chose numbers that are huge so that we couldn't actually just work them out by hand and factor and see if 13 divided into it. So we have to think about how we can do this. So we want to show 2 to the 74 plus 3 to the 74 is congruent to 0 mod 13. That's what we want to show. So I've just expressed it as a congruence relation. I want to show that 2 to the 74 plus 3 to the 74 is congruent to 0 mod 13. In other words, 13 divides the difference of those two numbers, which means it's 2 to the 74 plus 3 to the 74 minus 0, or just 2 to the 74 plus 3 to the 74. So what can we do? Well, first we're going to observe something. If I'm working mod 13, so I'm working with just remainders upon division by 13, let's see how 2 to various powers behave. So if I go 2 to the 2, that's 4 mod 13. 2 to the 4, sorry, not 2 to the 4, I want to go 2 to the 3 first. 2 to the 3, that's 8. So just again, mod 13. What's 2 to the 4? That would be 2 to the 4 is 16. But when I divide by 13, I have a remainder of 3. So 2 to the 4 is 13, or sorry, 3 mod 13. 2 to the 5. Now here's where things make it easier. I don't have to go 2 to the 5 is 32 and then figure out what it's dividing by 13. I can go, well, I already know 2 to the 4 is 3 mod 13. So I can just multiply both sides by 2. Because 2 is congruent to 2. And so I can do this fact that if I know two things are congruent, I can just multiply both sides of the two expressions together. So I get 2 times 2 to the 4 is 2 to the 5, and 2 times 3 is 6 mod 13. And what about 2 to the 6? 2 to the 6 is 2 times 6 is 12 mod 13. Oh, but I'm going to write it like that. That's negative 1 mod 13. And the reason I'm going to do that is because now I know if I took 2 to the power of 12, so if I squared the left-hand side, the 2 to the 6, I get a 2 to the 12. And what do I get when I square the right-hand side? What's the square of -1? Any ideas? Yeah, I get 1. So I've made a very quick leap to an expression that's going to help me immensely, because I know that whenever I have a 2 to the 12, it disappears because it becomes 1, and I'm just multiplying 1 by something else, so it never changes it. I can do the same thing for the 3. 3 squared is 9. 3 cubed is 27. Oh, but that's 1 mod 13. Oh, that's another one to keep in mind. And so now, when I go to 2 to the 74 plus 3 to the 74, I can say, well, that is 2 to the 12 times 12 goes into 74 how many times? 6 times, with a remainder of 2, and 3 goes into 74, so that would give me again 72. That would be 24 times, so that's 3 times 24, which is 60 plus 12, 72 plus 2. So all I've done is rewritten my exponents, 74, in 2 convenient ways, because this becomes a 212 to the power of 6 times 2 to the 2. And this next one becomes a 3 cubed, 24, 2 to the 2. Notice I haven't done anything with remainders yet, the work I've done above, other than just use the 12 and the 3. But now at this point, I can say, oh, that's congruent to 2 to the 12 is 1. And 3 to the 3 is 1. Mod 13. And so this is equal to 4 plus, that should be a 3. That's probably what was in the chat. That should be a 3 there, and this should be a 3 there. Yeah. 4 plus 9 mod 13, or in other words, 13 mod 13, or in other words, 0 mod 13. So what does that say? That says that 2 to the 74 plus 3 to the 74 is divisible by 13. Okay, so this is what's known as modular arithmetic. It's the arithmetic of the remainders, and that's what we've done here. So sorry I went a few minutes over. I'll stop the recording now.